Hello, everyone. How are you? So, just let me know if you can hear me fine. Awesome. Thanks. Okay. Today we will talk about the introduction to machine learning. Now, before we move on, I'm just wondering, how many of you are aware of machine learning, or knows about machine learning, or has any kind of experience with machine learning? You can just raise your hand, or you can just, let me know, by unmuting yourself. So, Ron, you do know about machine learning. That's great. Okay. Okay, then generally can you people let me know on the chat box probably, or maybe unmute yourself to let me know that what background are you coming from? Do you have any background from are you coming from programming background? Are you coming from mathematics background, engineering background, or there is no specific background, business background, or maybe completely new to this whole thing? Um, you know. That would be very helpful for me to kind of start the discussion around what machine learning is, because machine learning can be defined in extremely complicated ways and in extremely simplified ways. Uh, you know, so Gloria is saying nothing. Okay, awesome. So programmer, ex-computer scientist. Okay, now that's you see that's important for me to know. Okay, so there is a data analyst. Okay, so Sushil is a data analyst with some SQL background. Okay, perfect. Got that. Okay, so interesting. So Gloria is coming from a business background. Okay. Hmm. So I have general idea, took few tutorials, search. Okay, awesome. So I think yep. Agent currently a GPT scientist. Okay. Awesome. So what we can do is today, because we have diverse kind of audience over here, so let's take a little bit of a broader look at what machine learning is. In the beginning, I'll start with a very kind of I would call it a simplified explanation of what machine learning is. Okay. And then later on, what I'm going to do is actually start the notebook explanation for one of the computer vision problems, which is, let's say, digits classification. And we will develop together using PyTorch, one of the complicated machine learning algorithm, CNN, computer, vision kind of an algorithm for image classification. Okay. So I do not expect you to understand that code. I will share with you that code. I will very quickly go through that code. If somebody is already aware of that, I mean, they could ask question from me as well. But it would kind of give you a little bit of confidence that it's not that hard. But the main purpose is not that notebook, because I do not expect you to understand that notebook, because it is meant for someone who is already having a good understanding of machine learning. And As some people are coming here, with some kind of an introduction to machine learning, they probably want a little bit of deep dive into deep learning. So that's why I've prepared that notebook for them. But at the same time, I will try to cover I'll kind of try to cover different aspects for all of you. Okay, depending on your backgrounds. So someone did ask me a question. What is the GitHub URL for your CNN? Well, I'll share with you the link when I will go to the Colab notebook. So I will be doing it in the Colab notebook on Google Colab. Okay. I'm not exactly sure if you are aware of Google Colab notebooks, but I will let you know about that, okay, later on. But before I do that, let me take a whiteboard approach to explain what machine learning is, okay? So let's begin with this question that I'm going to ask. Usually, there are, as I said, different ways of defining machine learning, but this is something what I personally love the most, okay? So for example, if I ask you that there is a person standing at a particular height and wants to throw a particular stone, okay, from a particular height. Okay. And the question is how much time it would take for this stone, to reach this ground, right, which is at height h. Can somebody tell me, is it possible to give the precise time it would take for this stone to reach this ground? Can anybody tell me that? Is it possible to find out the time, to predict the time that it would take for this stone of a particular weight to reach this ground, which is at this particular height? Okay, somebody just, okay, not exactly depends on when. Okay, let's say you have all the information about the, okay, okay, so it depends on when. Somebody said S is equal to D into T. Somebody gave some kind of formulas for me, right? So one thing you will find here is that you don't need any machine learning here to do this prediction task. Can anybody tell me why not machine learning? Why did you give me those direct formulas, the Marshall, the PR, whatever the formulas that you're using? You can unmute yourself as well. Physics, exactly. So essentially, there are physical problems that you're dealing with, right? But all of those problems have been deterministically proven to follow some kind of rules, right? So these problems are now what we call deterministic problem because we can determine them, right? Using what? Using Newtonian laws, right? So you don't need any machine learning for that, right? Okay, imagine for now that we don't have any deterministic formulas and we don't have any Newtonian physics, right? Which will kind of allow us to calculate the time that it would take for the stone to reach the ground. Can anybody tell me what is the other way of doing this experiment and we will be able to predict the time correctly without use of any physical formulas, right? Measure, what do we measure? Sample, graph, fit. Yep. Okay. I mean, all of you are going in the same direction, but um, yeah, to some extent, yeah. So essentially, what you would do is you would repeat this experiment multiple times. You will have one stone with a particular weight, right? You will calculate the weight of a stone, right? And maybe then you will also calculate some of the other kind of variables. As somebody said, maybe it depends on wind, right? And maybe what is the height, right? And some other variables. For now, let's consider these three variables, right? And then you're calculating the time that it reaches the ground, right? So in this whole process, what will be the input features that we are calculating? Technically, we will repeat this experiment, calculating all the four things, right? What is the weight of a stone? What is the wind, height, time? And then you will do it for the second stone, third stone, right? And let's say you have 100,000 different stones, and you repeat this experiment for 100,000 different stones, right? It means now you can make use of this data to come up with some kind of relationship that exists between these three input features and this output feature time, right? Because this is what you want. At the end of the day, you want to predict the time based on the three input features. What is the weight of a stone? What is the height of what is the height from which we are dropping it? And probably what is the wind speed or something like that, right? So essentially, you see, if we were not having Newtonian physics, we still will be able to find out the time as a function of, time will be a function of three things, right? In this case, three variables: the height, the weight, the wind, right? Right? So this is what we call machine learning, right? We have some inputs, we have some outputs, and we have some training data containing input and output, right? We use this training data to find out this relationship that exists between the input and output. Why do we use the training data? Because we don't have deterministically proven laws which can capture this relationship. In case of this simple problem that I've discussed, it is relatively much more easier to use the Newtonian physics, right? We don't need really this kind of a machine learning experimentation, right? But there are so many things for which we don't exactly know how they behave in the real world, right? There is some kind of a probabilistic, there is some kind of a probabilistic, um, you know, elements in the process, right? In that case, we can't use deterministic laws. We have to use machine learning, which will capture these probabilities, right? So, for example, if I ask you to predict the stock price, will you be able to do it? Not possible, right? Why? Because there is a lot of probabilities and a lot of factors, random factors affecting the stock price. You cannot have a single formula which can tell you that, hey, this will be the stock price prediction. So there is so many input features, input variables which are affecting the output. So you can take a lot of data to predict the stock price, right? Then the next question would be, again, there are so many other things. Predicting, predicting the price of a house. Let's say, again, this is a very simple problem, but can you predict exactly the price of a house? No, there are so many factors which is affecting the price of a house that it is not possible to create a single deterministic formula, right? So for that reason, you design an experiment to collect different kind of data and then use that kind of training data to come up with some kind of a machine which will capture that pattern. Any question around that? Now, I'm just wondering if anybody is having, I mean, again, I understand every one of you are coming from a very diverse kind of a background. So I'm just wondering if anybody is having any kind of a question around this very simple kind of a interpretation of a machine learning algorithm as what machine learning is, generally speaking. No? Okay. So okay, so I am assuming there are no questions. Okay, so if there is no question, then let's continue with this. Now let's think. Okay. Now the example that I gave you, by the way. So now I'm gonna shift my gears toward those people who are relatively more aware of machine learning. Okay, so bear with me. For those of you who are not very well aware, please bear with me because I have to take care of those as well who are a little bit aware of machine learning. Okay, so the example that I just gave you comes under the category of supervised machine learning. Okay. Usually, you have different types of machine learning. One of the type is called supervised machine learning. And this example that I gave you where I have the input and I have the output, right? And I try to find out the relationship between input and output is what we call supervised machine learning. Why? Because this relationship, finding this relationship can only be done by using this output that we have, right? If we are not having any output, how can we find out this relationship? It is not possible for us, right? So this supervision is being done by using this output, okay? More mathematically speaking, this relationship is found out in this manner, where we have some kind of a model, right, which will do the prediction for the input, right? And this prediction will definitely not be a perfect prediction, right? It will not be exactly the same as we have the output for this input, right? So this prediction will be having some error, right? So there will be some difference between the output that we have for the input and the prediction that we are getting from the model. This is what we call error. right? Now, given this error that we have over here, what we need to do is we need to find out a better model. We need to find a better model which will reduce this error, right? So basically, what I'm doing over here is using the outputs to find out the error and then try to change the model and find a supervised machine learning model which will eventually give me the prediction such that it is closer to the original outputs, right? Which means that we are actually trying to reduce the errors that we have, okay? Now, somebody did write something. So loss is equal to the function of error. So this is your question. Can you let me know? Is error also okay? So this is is error also referred to as loss? Exactly. Loss is not a function of error. Loss and error are the same thing. Okay. This error that I'm calculating over here, right, is you can call it a loss, you can call it an error, whatever you may call it, right? But this error is a function of what? Well, this error is a function of two things because this error is coming from the predictions that we have and the actual output that we have, right? Because when you subtract both of them, you will get the error, right? So the error or the loss is a function of the prediction. But quite interestingly, what is prediction a function of, right? What is a prediction a function of? Well, if error is a function of prediction, prediction in itself is a function of a model that we are using. Let's say we are using a linear model. In that case, the prediction y hat, this is a prediction, is going to be mx plus c. This is an input, right? This is the intercept if you're using a simple linear model. This is a slope, right? So changing this slope and c, changing these two values, given the input x, we can change the predictions, right? So technically, f is equal to mx plus c minus the actual output value. And again, there is a little bit more kind of a mean squared error, but for now, I'm just considering a simple error, right? So, which means that error or a loss is a function of this m and c, right? So it means we have to find the best m and c such that this error is minimized. Finding best m and c also mean finding the best model, right? Any questions around that? Well, so somebody did comment in the in the chat, said that I think loss is typically defined as mean squared error. So mean squared error in that case, loss is equal to the function of error. Well, again, I mean, what is error? Again, as I said, I mean, you can call you can make it two-step process where you can say loss is equal to error squared and mean of it, right? But essentially, why I'm calling loss and error the same thing because they are technically, you can again, I'm kind of differentiating between this. When I'm saying error, I mean the difference between the prediction and the output values, right? So I will call it a loss. Again, it's a technical term. Some places you will use this terminology that loss is a function of an error. But eventually it will come down to the whole logic that I just explained, which is, okay, if loss is a function of error, error in itself is nothing, right? What is error dependent on? Well, error is dependent on actually some prediction minus the output, right? That is what error is. If you are taking the square and mean, that is additional stuff. But the variable that it is dependent of, and you say it is a function of something, it means you're interested in the variables at play over here, right? So the variables at play is only prediction because output is also constant over here, right? So then you may call it error separately over here. But again, you can call it a loss dependent on prediction, but prediction is mx plus c, and the variable again is m and c. X is also not variable. So technically, again, loss is a function of M and C, right? At the end of the day, right? And again, as you said, we can take the square and the mean for various reasons. There are other error metrics as well for classification. We have different error metrics, cross entropy metric, and so on as well, right? But the square is for that particular reason. Yeah. Okay. So going back to the original discussion that I was having, which was that this is how supervised machine learning model works, right? Now, just giving a little bit of more context, right? For those of you who are more interested, um, how do you, as I said, you know, the loss or error, whatever you may call it, is equal to the mean squared error, right? So which is 1 by n summation of I is equal to 1 to n, right? Which is again y hat minus y. Uh, Again, this is ith sample and then squared, right? That would be the exact kind of a definition. This is a prediction. This is the true value, right? I'm not, I want to go through this whole thing a little bit faster, right? So if you are interested in the mathematics of it, let's say, right? Although I would not encourage you at this stage to go to the mathematics, but let's say I want to get into the mathematics. So it's not that hard because at the end I said that I want to find out how do I change the M and C, right? Well, you can use the gradient descent, which is all about partial derivatives, right? So if you look at the loss, let's say this is the loss on y-axis, and this is the M slope on x-axis. And let's say we have this kind of a relationship that exists, right? So let me just change this relationship in this manner, right? And right now I have this M over here, right? Which is this kind of a loss. So what should I do? Should I increase the M or should I decrease the M to get a minimum loss? Yep, you have to move in the left direction, right? Well, in that case, if you have to move in the left direction, then in that case, what will be the how do you determine that? Visually looking at it, right? But mathematically, you can just find out the slope at that particular point, and that slope would determine if you should move on the left direction or the right direction, right? Um, Let me just move. And if, let's say, you have a mean squared error over here, then what would be the situation, right? Should I move to the right or to the left? Right, yeah. Okay, so somebody said I have so there are a lot of comments. Marshall said they spread error measurement across multiple n samples. Yes, exactly. That's why we are having mean squared error, right? Again, depending on if you're using batch gradient descent or stochastic gradient descent. Somebody else said I have heard squared errors is out of fashion. Direct error is often preferred. Probably no. No, that's not the case because you have negative error and you have positive errors. You don't want to cancel them out. So that's not the case unless you're suggesting something else to not kind of negate both of them. I don't think so. That would be the case. So yeah, over here, as you said, that we have to kind of increase the value of M. Again, you can see that it's because of this slope value, right? So these slope values at a particular location would definitely be very important to determine. Okay. Let me just move a little bit over here. Let me just close whiteboard and again pick the existing whiteboard that we have. My whiteboards, that is so weird. All of my whiteboards are gone. Okay. Yeah, you can take the absolute error as well. Yeah, you can take the absolute error as well. That would be a mean absolute error. So yeah. So the loss that I have defined is a mean squared error, which is I'm summing I is equal to 1 to n. As somebody suggested, I can take the difference, which is y minus y hat or y hat minus y, right? And then you can either take the square of it, right? Or maybe take the absolute value of it. You can do both of those, right? This one is called a mean squared error loss, right? There are different losses that you can use nevertheless. But if you want to take the partial derivative of a loss with respect to m, then you can simply go on and find out 1 by n, I is equal to 1 to n, right? What is y hat? It is mx plus c if you're using a linear regression, right? And then this is going to be y, right? You take again the square of it. Well, now what? How can we change the m? You have to find out the derivative with respect to m. So derivative of loss with respect to m is going to be 1 by n summation of I is equal to 1 to n. And this term can be considered as x squared. So the derivative is going to be 2x, right? So it will be mx plus c minus y, right? And then internally, you also have to take the partial derivative of this internal term, which is mx plus c minus y with respect to m, right? Okay, if that is the case, then what do we get as a partial derivative? Well, the partial derivative is going to be 1 by n summation of I is equal to 1 to n 2 into mx plus c minus y. And if you expand that, the partial derivative of mx with respect to m is going to be x, and plus the partial derivative of c with respect to m is going to be 0, and partial derivative of y with respect to m is also going to be 0, right? So at the end of the day, what is the partial derivative of L with respect to m? It is going to be equal to 1 by n summation of I is equal to 1 to n 2 times, right? mx plus c is y hat minus y multiplied by x, right? So I can just move on over here, and I can just show you that finally, if I just take these terms out, so it is going to be 2 by n, summation of I is equal to 1 to n, right? Y hat minus y multiplied by x, okay? So it means that this is the partial derivative. I'm going to call it d of m, right? Partial derivative with respect to m, right? In gradient descent, I said that we will be changing the m, right? Based on the error. We want to reduce the error, right? This partial derivatives is going to give us the slope, and then the new m is going to be equal to the previous m that we are having. This is the previous m that we are having, right? And then minus, right? What is the direction of movement, right? And that would mean that we would either reduce or increase the partial derivative depending on this term being positive or negative, right? And we will also multiply this with alpha. Alpha is a learning rate, basically. It is a relatively small number, let's say 0.01, so that the movement of improvement is very small, so that we don't kind of jump directly and change the value of m a lot, right? Now, that was a little bit of more detail and too much of a detail, but this was just intended for those of you who are already aware of this whole process and wanted to know a little bit more about the supervised machine learning, okay? So this is the core basis of the supervised machine learning, okay? Any questions around that? AI wrote those simple Python scripts to train a two input. I think the assume the differences are caused by the method of random initialization of the weights and bias. I generated synthetic training data and test data based on sin x. Sometimes the training drops the loss to near zero. Otherwise, the training fails to minimize the loss. I fixed the training data and test data. I assume that the differences are caused by methods of random. Probably. Not exactly sure, because there will be a little bit of more detail that I have to look into as what are the problem that you're having. But nevertheless, again, it would require a little bit of an understanding and a deeper look into your problem at hand, which would not be kind of the thing that we will be doing in this session. But yeah, we can have a look at some other time probably, because this session is all about introduction to machine learning, and And a lot of participants probably might not be aware of what you're talking about, maybe not even aware of Hugging Face. So we have a variety of kind of a participants. So that's why I probably will not be able to spend time with that. Maybe at the very end, I can have a look at that as well with you. Okay, Marshall? So yeah, okay, awesome. So as I said, we did talk about the supervised machine learning algorithm, right? That is a very simple kind of a algorithm, right? A set of algorithms. Within the supervised machine learning algorithms, you have two types of problems. One is called regression, right? And another one is called classification, right? So what is regression and what is classification? Well, regression is a problem where the output is containing continuous values. Okay. And classification is where the output is a categorical variable, right? For example, if I tell you to predict the score of the exam score based on the number of hours of sleep, right? So the X is the number of hours of study, let's say, right? And then I'm predicting the exam scores. Is it going to be a classification problem or a regression problem? Anybody? It's a regression problem, right? Because the output over here is continuous values, right? Usually you will fit a linear line on top of that, probably, if it is a linear problem, right? You will call this model a linear regression as we talked about, right? That is one of the simple machine learning models, right? Now, let me change it a little bit. And if I have to predict instead of exam scores, right? If I have to predict, let's say, if somebody did pass or fail, depending on the hours of study, right? So these are all of the student who did pass, and these are all of the students, let's say, who did fail, right? So is it a regression problem or a classification problem? Classification problem, right? Because I'm predicting a category over here, right? So the classification line which would differentiate between both these categories is this simple line, right? So anything to the right of it is pass category, right? And anything to the left of it is fail category, right? And this linear line that I have kind of put it in between these two set of points, this is this model that I've used over here is called logistic regression. Okay. Now, these two are very basic fundamental machine learning algorithms that you would learn almost every time in the beginning of any course. Okay. Um, Although there is a word regression, but it is not a regression. Okay. Basically, it's a classification algorithm. Okay. So now, without getting into the too much detail about the logistic regression, I will just nevertheless say one very important thing over here is that for the linear regression, the model is mx plus c, right? The loss is mean squared error, which is 1 by n summation of I is equal to 1 to n y hat minus y square, whatever, right? And then you find out the partial derivative of m and partial derivative of c using the calculus that I just talked about, right? So usually in any machine learning supervised regression and classification case, you have some kind of a model. If it is a parametric model, right? You have some kind of a model, right? Then you have some kind of a loss function that you define, and then you use that loss function to optimize for the parameters that are used inside a model, right? That's the usual workflow. Okay. Now, if you look at the logistic regression case, it is also very similar. The only change is that instead of y hat, the prediction that you have is instead of mx plus c, it is going to be some kind of an activation function, which is sigmoid activation function applied on mx plus c, right? And if I just open it actually explicitly in the mathematical terms, it is going to be 1 divided by 1 plus e power minus mx plus c. Now, this is done to make sure that the predicted values are between 0 and 1. Because it is output, we want the prediction binary classification, so between 0 and 1, right? That's the major difference, right? And then the next difference is, apart from model, once we have the model, a model is a little bit different than the linear regression one, of course. Then the loss is also different. This is also called, cross entropy loss, okay? There is a whole discussion around it. Again, we will be having a separate lecture if we want to talk about logistic regression. It's not that easy to explain it over here. But essentially, you have minus y hat into log of y minus into 1 minus y hat into log of 1 minus y. Okay. Now, this is a very interesting loss function instead of a mean squared error loss function that I talked about, right? There is a reason for this loss function, which requires details, which I'll not get into the detail. Okay. Now, again, because we have m and c again, so you will find out the dm and dc by taking the partial derivative of this loss function with respect to m and with respect to c as well, right? So there is again some calculus involved over here, which I'm not going to get into the detail for now, okay? Because this is not the lecture for that. But this is just to let you know how machine learning works, okay? Now, if that makes sense, then let me know. I'll just quickly go through the deep learning part and we'll show you how you can move from the machine learning to deep learning. Any questions on that? If not, then I will directly go to the deep learning. So until this point, I've shown you that you have some kind of an input, you have some kind of an output. In between, there is some kind of a machine learning model. That input goes to this machine learning model that gives you some kind of a prediction, y hat, and then you use this prediction to calculate the loss, right? Using the actual values y, right? And then you go back and modify this kind of a machine learning model, right? That's the usual case that I've talked about. Now, this model, that you're using can be a linear regression model, can be a logistic regression, can be other kind of a model, right? But that's the usual case, right? Now, understand this. Imagine you have X, you have Y, and all of these samples, let's say that I'm drawing over here, is class 0, and all of these samples are class 1 outside this densely populated area, right? Now, to differentiate between these two classes, what do we need? Can we differentiate it using a single linear line? Can we do that? Anybody? If this is a separate class and this is a separate class, right? What do we need? So what kind of a decision boundary we need? Circular, right? We need a decision boundary which looks like this, right? However, if I try to apply a logistic regression, you might find this linear line, right? Maybe you find this linear line. Maybe you find this linear line. Maybe you find this linear line. Doesn't matter, right? But at the end of the day, you will not find any nonlinear lines because logistic regression cannot give you a nonlinear line. But if you combine multiple logistic regression, can you get a nonlinear line? Well, yes. Imagine you have this linear line, you have this linear line, this linear line, and this linear line. So circle can be approximated by 4 linear lines, technically speaking, right? Even with 3 linear lines, but consider 4 linear lines, right? So if I combine 4 logistic regressions somehow, I can achieve this complicated nonlinear decision boundary, right? So I can stack multiple linear lines to get nonlinear line, right? So maybe I can just stack these models, these simple models, right, over here, right? And then the final prediction can be from combining all of them, right? Does that make sense? Now, I've tried to move from a simple linear regression to logistic regression to neural networks, right? So this is the simplest neural network you can have. Okay? What is neural network? It is just stacking of these linear models to get the output. You have an input layer, right? You have some kind of a hidden layer which contains these simple neurons. or you may call it a models, and you have output layer. Does that make sense? Any questions around that? The size of a hidden layer would determine the complexity that can be modeled using this machine learning model, right? Imagine you have only four kind of neurons over here. So maybe you have, let's say, four different kind of parameters or eight different parameters that you're learning for now, let's say, right? So the complexity is not that much. You're only able to get four linear lines, right? Which can approximate the circle, as I said. So this four parameter can do something like this, which simple logistic regression was not able to do it. Now I want you to imagine what for what 100,000 parameters can do. Imagine what 1 million parameters can do, what 100 million parameters can do, and then what 100 billion parameters can do. Can anybody tell me how many parameters are there in GPT-4? The chat GPT that you're using, how many parameters in that neural network is there? Anybody? Yes. Well, I'm not sure if it is 2 trillion. Not really sure, to be honest, but I think so. It's GPT 3.5 was, I think, 175 billion, if I'm not mistaken. Yeah, 175 billion. Even now, again, that would move us to a separate discussion. But even the local large language models that you can try on your computer for free, the Llama, the Mistral, and so on, they have now 48 billion parameters, right? You can make use of 48 billion parameters and run this model locally on your own laptop. Okay, you don't have to use ChatGPT. There is a way of doing that, but forget about doing that. I'm just letting you know one important point here, that the number of parameters would determine the complexity that it can contain. But the more parameters that you're using, right, what does that mean? You will need more and more data to learn these parameters, right? So the more training data would be required to back propagate and learn the parameters the way I kind of explained, right? Um, I think you can. I'm not sure if it is a 48 billion or 4.8 billion, but I think you can, Terry. 7 billion, yeah, probably 7 billion, yes, but for 48 billion, there is a way of decreasing it. Although it is a 48 billion parameter model, but there is a way to decrease it, like compress it and use it on the runtime. There is a way of doing that. I don't exactly know the quantization to 2-bit. I think quantization uh, apart from quantization, there is another kind of optimization methods that you can apply on that as well. The performance are still really good, comparable to 48 billion parameters. Yeah. Okay. But the point over here that I'm trying to make over here is that you can make use of neural networks for really complicated reasons as well. Okay. Now, finally, um, finally, I will just move again. That's not a discussion of the large language models. Otherwise, we will get into that detail because there are a lot of people who would probably not even aware of what we are talking about here. So what I'm gonna do instead is just kind of give you a quick kind of introduction, and then I'll just share with you the link to the collab, which you can work on your own as well, right? For those of you who have already the experience of that, right? So, for example, um, what you can do is, let's say, for example, you can get the neural networks that I talked about, right? And make it work for the language data, right? You can make it work for the vision data, all right. So there is different ways of modifying the neural network to make it work for these different kind of data set. You can make it work for the speech data, right? Because you have different kind of data set, right? Until this point, I've only talked about the tabular data set where you have some kind of a columns, some kind of a samples, and so on, right? But language data is in the form of a text, right? Vision data is in the form of images and videos. speech data is in the form of a signal, right? So how do you deal with this? Well, you can convert them into this tabular form. You can do that, but it will not be that efficient. And neural networks, on tabular data is not that efficient. Instead, as an introduction, the special kind of a neural networks which deals with the language data is called LSTM, right? Basically, in the beginning, it was the RNN architecture, but then, a more modern kind of architecture was developed, which is called LSTM. But then, actually, everything changed with this new architecture called a transformers architecture, right? Which was developed, with the paper "Attention is All You Need" in 2017, right? And because of that architecture, the whole kind of game changed for language modeling, right? So although I showed you what neural network is, but because we don't have much of a time, I cannot get into the detail of the different architectures that are being used for the language data and how it is being used for all of these different kind of architectures. Okay, so you have RNN, LSTM, and transformer architectures. Okay, now if I just yeah, this is the name of the paper. Yep, yeah, this is the name of a paper. Okay, so let me move a little bit to the down over here. Yeah. So if you look at the vision model, in the vision model, you can have a look at different kind of algorithms that are being used, right? So for the vision model, you would see, let me see what is being written by Martian. So yeah, Attention is All You Need is a paper not just by Google, but there are other developers from some university as well. And again, and yeah, again, you can also look at some other. There are so many other papers, but the Attention is All You Need is the paper where it all started, right? There is GPT papers as well. There is Facebook Llama papers as well. There is so many other papers that came after it, but I think so. The core of every single thing is this single paper. Attention is All You Need. If anybody wants to read it, you can read it, but it will be very difficult to and hard to understand. So I would not recommend right now, okay? Because it explains the transformer architecture. For that, you need to know what is LSTM, and for that, you need to know what is RNN and so on, right? So it's not that easy paper to understand, okay? But nevertheless, for the vision model, you can also have a look at different kind of architectures, right? For the vision model, we have what? Well, for the vision model, we have a special architecture called convolutional neural networks, okay? Now, this is a special neural network, right? Which is used to deal with the images, right? And videos, right? And and after convolutional neural networks, you can also look into the vision transformers as well, by the way. Okay. Vision transformers is also being used. But today I'm going to show you the use of convolutional neural networks in PyTorch, right? For speech, you can also make use of this transformer and the LSTM as well, because it's again a sequential data. Okay. So that's it. Now I will just quickly go through the notebook, okay, which explains the convolutional neural network application. And I do not expect you to understand the code over here. Let me actually first of all share with you the code. Please let me know if you can. Yeah, I hope so. You can see the screen. You can look into the notebook. Okay. So over here we are just trying to classify different digits. Okay, with this architecture called LANet. That's the very first architecture that was developed in 1998 or something like that, right? So we are just importing the PyTorch. Again, PyTorch is a framework which allows you to work with neural networks in much more efficient manner. I think so. It will be um, I mean, I've chosen this very hard topic probably for the practical purposes, just because I'm not very well aware of I was not very well aware of the kind of audience that I'll be having, because I have mixed kind of expertise over here. So I've kind of chosen this particular topic. But definitely, we can look into some other simple scikit-learn kind of a model as well. But you can work with this. You can import these libraries, right? Load the data set over here from the torch, right? And then you can use the data loader, right, to load it one by one, right? And then try to understand the data. At the end of the day, every single image is nothing but just a NumPy array, right? If you look at the data set size, you have 60,000 different images. Each image is of a size 28 cross 28. It's a grayscale image, right? And there are images of these nine different digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? The images look like this, right? So this is an image of 9, 9, 5, 4, 4, 1, 1, 4, 5, right? So you can find out different images and their associated labels over here, right? And then after that, you will have a train loader iterator, right? This is just to let you know how we will iterate over the train loader, because it's an iterator, right? And why we need iterator? Because in Python, if we load all of the data into a memory, it would crash the memory, right? Because sometimes we have 60,000 different images, and each image contains about 784 different numbers, right? And each number is, I don't know how many bytes, right? Depending on how floating point number or what kind of a data type is being used, right? So depending on that, if you load every single thing into a memory, it's not that efficient. So usually you would load every single thing one at a time. You would not load everything into a memory, right? So that's why we are using it as an iterator, right? And this is just to kind of show you that this is an image of a five, where we are going to extend it to 3 dimension, where the first dimension is the color dimension. And because it's a grayscale image, so we have only 1 dimension over there, right? We have 32 batches, which means in a single batch, we have 32 different images. And each image is of shape 1, 28, 28, right? And for 32 different images, we have 32 different output labels as well, okay? Then for the training part, we are just asking if the GPU is available. If it is, we will just use that, otherwise not, right? We'll set the hyperparameters over here, in which case I'm just saying for how many epochs we want to go and what is the learning rate we want to use, right? We will be storing all of this information in this list. This is the kind of convolutional neural networks. As I said, we don't have much of a time to explain the convolutional neural networks because this is kind of an introduction. I'm covering too many things over here at once. So of course, I will not get into the detail of that, but essentially it's a very nice idea of making the spatial kind of information, making use of the spatial kind of information in the images for getting the predictions. Okay. Nevertheless, if you just have a look at the whole thing over here, you can get this information from their original paper as well. But this is something you would get. The filters, the strides, and this is something related to PyTorch. I don't expect you to know unless you're already aware of the PyTorch, but it's not that hard. You can just look at a few lines of code. Within this few lines of code, we will be able to, do the whole thing. This piece of code that I've written over here, right, is exactly the same, right, would do exactly the same thing as this piece of code, right? Now, I've done it in two different ways, is to explain as PyTorch can be, you can create a code with PyTorch in different manner, and it would give you the similar kind of result. You don't have to worry about it, okay? So in these few lines of code, you have defined the whole complicated architecture, and you don't have to worry about all the mathematics and so on, right? And that's the beauty of PyTorch and deep learning, right? Now you can initialize all of the weights, right? And then over here, you have just created a model, right? This is how it would look like. You will set the optimizer, right? And the loss function, as I said, it's a classification task. So it's not a mean square error loss. Instead, it's a cross entropy loss that we will be using. And then we'll use a stochastic gradient descent, which is a way of finding the optimum parameters, right? The weight parameters, right? And so on. Then finally, we will define a train function where we would just go through this whole thing multiple times. Well, you can export it from using the file and then go to download and say download.py. That would download the whole thing into a Python script, hopefully. Okay. So yeah, you can get that whole thing over here. Like this is a training kind of a function where you will just get the input and outputs. Then you will get the prediction using the model. Then you will calculate the loss. you will calculate, and then you will take the partial derivatives over here. You don't have to do the mathematics. You just call this function. It will do all of the mathematics for you. And then you will just update all of the parameters over here, right? In this kind of a function. Okay. So this is a test data. Again, it would take the prediction and would give you the prediction with maximum probabilities, right? And so on. Over here, I'm just training the model, right? It increases the accuracy and so on, and it reaches the accuracy of, if you run it, it would take a little bit of time, but it would eventually, reach the accuracy of about 80%. Okay. And so on. And finally, you can see that the prediction is 3 for the image 3, right? So you can run this yourself. Hopefully, it will not give you any error, and you will see, this whole thing at work. Okay. You can look at a simple scikit-learn kind of examples online as well. That's why I chose a little bit of different kind of a problem, which will be a little bit difficult for you to find online. Instead, that's why I kind of chose this particular problem, which covers many aspects of deep learning, which is advanced kind of a machine learning. So I tried to cover very basics as well as a little bit of complicated part of machine learning. Hopefully you enjoyed it. But yeah, if you have any question, please do ask me. Marshall did ask me a question. So this is OCR using CR. No. This is not OCR. This is a simple classification task. Given an image, I want to classify the image into one of the 10 categories. If this image is an image of a digit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? OCR would be optical character recognition. Okay. That's a separate thing where you have a scanned images, and from scanned images, you're recognizing the characters, right? That you're extracting the text from the images. That would be a completely separate task. Okay. So yeah, if there are any questions, please do let me know. Otherwise, I would encourage you to have a look at the WeCloudData, different kind of boot camps that we offer. We offer machine learning engineering, data science, ML ops, and so on. So we provide different kind of boot camps. So do look into that as well. If you're interested, just message us. We will kind of explain to you what kind of work we are doing and what kind of projects we are working on, and how can we help you in your whole story. Okay. In your whole pathway, in your career pathway. Okay. So yeah, if there are any questions, please let me know. Otherwise, have a nice rest of the day. Take care. Thanks, Ron. So Marshall is asking, these simple Python scripts to train a 2-input MLP neural network, hidden parameters are user changeable. I generated synthetic train data and test based on SINX. Sometimes the training drops the loss to near zero. Other times the training fails to minimize the loss. Yes, there is a problem with the initialization. Yes, you're right. Uh, um, you have to be very careful with the initialization at the same time, because sometimes it is stuck somewhere, right, in the local optima probably. It is not getting out of it. But yeah, so yeah, you can definitely look into the initialization and some other activation function as well, Marshall. Sometimes the activation function and so many other things are also kind of important in that sense to get out of it. Okay. So yeah, everyone, take care and have a good rest of the day. And yeah, take care. Yes, it does permanently stuck at local non-optimum. Yep, it is quite possible. So the initialization has a strong effect. Yes, in getting the global optimum. Okay. Okay, everyone. Have a good rest of the day. Take care. Bye-bye.